Thank you. Next up is Mike Lockwood. He's going to give us a talk about why our stars are not round, or I don't know, why not my stars, but why your stars may not be round. Mike is an electrical engineer and professional optician. You went to Illinois Institute?
Illinois.
Illinois for a master's degree at University of Illinois Champaign, right? Yeah. So I'm going to go ahead and you can start up. No, this is for you to illuminate you.
Oh, okay. I see.
You want to be illuminated, or you want to be in the dark?
I can see fine, so that's good.
Okay.
Okay. Well, thanks for coming. I'm always very happy to present here at this star party because of the conditions that we get weather-wise. They really allow optics to perform up to their true potential, and that's what I'm all about. I want people to push their optics, and no better place than this. So thank you to all the staff for putting this event together for the 30th time. It's just wonderful. So I'm going to talk about basically Newtonian reflectors. I'm not going to talk too much about other telescope designs since that's the majority of what people have for visual use. And I'm going to try and give you a debugging guide to help you track down problems that may pop up or may come and go, or just explain some phenomena that you see in your telescope through your eyepiece. And there's an example on the board here of what we call an aberrated star image. It's got several distortions that are on top of each other, and we're going to talk about this diagram later on in the talk after I've given you some background. So there is an online version of this talk, but I'm not going to give you the link until after the talk because I know people will be on their phones like this. Oh, no, it's harder than that. So no telescope is perfect. Some get close, and some are much closer than others. And there are always little strange things that go on or little sources of error in the optical system. We can have problems with collimation, which I'll talk about. Thermal issues, which are hopefully the next major talk that I do at star parties. I've got so much data on thermal issues with telescopes, I've got to put together a talk about that. I'm really excited to share that in the future. Optomechanical issues, which is basically what happens when the mechanics of the supports for the optics don't work so well and actually bend the mirror a little bit. That causes distortions, and it's more common than you think. Optical issues I'm not going to really cover here. I'm going to talk about one thermal issue that has to do with optical quality, but I'm not going to talk about mirrors and their figures, really. Design problems, if the mirror cell is built poorly, I can't talk about that because there are too many cases. We'll just talk about some of the symptoms of cell problems. And of course, the kicker is that there are usually combinations of more than one problem. It's what Dick Suter in his book about star testing calls the wobbly stack of aberrations. All these things add up and get on top of each other, and you end up with that mess of a star image that I showed you at the beginning here. But hopefully by the end you'll have a little bit of an idea about how to break that apart into different aberrations and see what's going on. So here it is again. This is a defocused star image from a Newtonian telescope. It's a simulated image. We can see that there's sort of a weak center spot here. It's brighter on this side, and it's got kind of a funny shape. We'll talk about all that. And that's on one side of focus. You can look at images on both sides of focus, and sometimes you'll see things flip and become the opposite, and sometimes you won't, and we'll talk about why that's important. This is a combination of, I think, 3 or 4 aberrations plus some simulated atmospheric turbulence, which we can't get rid of. But here, you have the best shot at getting really good atmospheric conditions that let you see more of what the optics are doing and less of what the atmosphere is blurring out. And there's a lot of things. The best thing about this is most of the stuff that you do to fix these things they're often free. They're just simple little fixes. You just need to know them and learn to recognize them. So here's our playbook, if you will, for figuring out what the heck is wrong with your telescope. First thing, learn to collimate it properly, and I'll talk about a little technique for that. Next, go through and inspect the optical supports and holders for mechanical issues. You're looking for mirrors that are in a cell that have no room to move, that are being pinched by their edge supports or whatever else might be in the telescope. All kinds of funny things happen when you transport a telescope. Things vibrate, screws tighten, screws untighten. We can rotate the primary mirror, and this is one assumption I'm going to make, is that your mirror is not glued in. And you can actually have enough looseness in the cell that you can rotate that primary mirror and see if what you're seeing rotates with that mirror. That's a very important ability to have in debugging. We can turn on or off our cooling fans if we have them and observe this effect over hours, because often fans will set up a cooling or a temperature gradient in the mirror, and that can take an hour or two to actually redistribute itself. If you've got a cold spot and a warm spot, those have to exchange heat until the mirror reaches equilibrium. So things may not instantly go away. We can learn from others' problems and help them. Please share this with your friends and help them fix their telescopes. I hope that more people will learn these skills and have a lot more fun at star parties. Be willing to experiment, because you're probably not going to hurt your telescope unless you drop something on the mirror or drop the mirror. So little experiments here and there, playing with collimation, loosening edge supports and that sort of thing, may, it may fix the problem very simply. So don't be afraid to try. And at last resort, what I do is I work on optics. If you can't figure it out and all the tests sort of indicate the problem is in the mirror, then it's time to have the mirror or the mirrors tested. So here are the ground rules if we're going to go through this procedure. And there are a lot of possibilities, and I'm trying to cover them in the most logical order possible. So if I say something that doesn't make sense to you, ask me a quick question. I'm going to take most of the questions at the end. So the first thing, put the star in the center of the field and keep it there. That's because the center of the field is the optical axis, and that's where the least distortion is going to occur from aberrations of the telescope system, the eyepiece, and possibly the coma corrector. That's called the optical axis, the center basically. The optical axis is a line coming out of the primary mirror at a right angle to that particular spot in the primary, a normal vector, if you call it in engineering speak, bouncing off the secondary and going to the center of the focuser if everything's lined up right. If you've got the ability to track a star, use it. Drive system is very important for keeping the star in the center of the field. You can see more things as you do your testing. Number two, check your eyes for astigmatism. How many of you know your eyes have astigmatism? A lot of you. So you know that's there. You can rotate your head, star shapes change a bit, and you're just used to that. Or you get a dioptrics, or you wear your glasses while you're observing, and hopefully that reduces that quite a bit. If you don't know, you can look at a star at somewhat low power and rotate your head. And if the astigmatism you see rotates with your head, it may be in your eye. There's also another possible source of that. Then you want to increase the power and see if you see astigmatism at the higher power. If it's still there, chances are it's in your eye, and it's not due to the exit pupil, which I'll talk about later. Exit pupil. This fools a lot of people. So you can picture the eyepiece as producing a bundle of light that comes out and you look at with your eye. If that bundle is larger than what you can fit into your eye, or larger than your pupil, which is going to expand at night and get, hopefully 4, 5, 6, 7 millimeters in diameter, if you can't get all of the light into your eye, it's going to have some effects. It's going to make the image a little bit dimmer, but it also may distort star shape. So if you see a funny star shape, move your eye around the eyepiece with the star focused and defocused, and see if the shape of the star changes. As you move off to the side, you may see a very different shape than you see in the very center. And this is just a test to see if you're getting all of that light flown into your eye. Here's a crude picture. Here's an eyepiece, and here's a cone of light coming out. This black line represents what's going to clear the opening of the pupil. This is not optically correct. It's just for demonstration purposes. This yellow light, though, is going to hit the pupil and be blocked. It actually won't make it back into your eye. So you're basically stopping down your telescope, which is fine. You can observe at low power and look at large objects. You're just going to lose a little bit of light, and the stars may have a funny shape. But we don't want to confuse this funny shape with something actually being wrong with the telescope. So for example, here is a simulated defocused star image from a 16-inch outflow reflector. And if the exit pupil is too large, I'm just going to do something very simple here. And I'm going to block part of it. So this is what you would see if your exit pupil was kind of small and you couldn't see the whole image. And I'm going to get down so everybody can see this. You see this when you move your eye around the eyepiece, your exit pupil is actually quite large, or something else is going on, and you're not seeing the whole defocused star image. So that fools a lot of people into thinking that the star isn't round, and it's really just their own eye blocking some of the light. So rule number 4 and 5 are the last two rules. We talked about this a little bit. If it's early in the evening, or the temperature is changing, chances are you're going to see some effect of that. You're going to see air currents and turbulence, possibly within a tube if you have a tube telescope. If you have a truss tube telescope that's open, you may see warm air eddies going around the face of the mirror, causing distortions. And these will all reduce as the mirror equilibrates and gets closer to air temperature. You're going to see a change in the mirror correction, generally, to what we call overcorrected, and I'll talk more about that a little bit later. And this is normal for an accurately corrected, accurately made Newtonian primary mirror to show some overcorrection in the star test as it cools off. Now, I've always maintained that one of the reasons that this place is better than other observing sites is not just for the quality of the seeing, but also for the quality of the mirror cooling. The temperature doesn't drop as much at night. There's usually a breeze, and that allows the primary mirrors to track the air temperature more closely than definitely in the Midwest, where the temperature just drops like a rock sometimes when the sun goes down, especially in the winter. So, two advantages here. As the mirror cools, and we'll talk about all this more, a change in secondary shape can also occur, and that can cause some temporary astigmatism while the secondary mirror cools off. Or if you crank up your dew heater, you can actually warp the glass by heating it and expanding it and cause astigmatism that way. Lastly, I already talked about this. Make sure your mirror, if possible, is mounted in a cell where you can rotate it, because this is a key to the diagnosis of where the actual problem is. So those are the rules. Operating on those, we can talk a little bit more about some of the properties of glass and how to debug the system. So mirrors are made of glass. It's a very stable material. Over time, over 100 years, it may not change shape hardly at all, imperceptibly, a tiny fraction of a wavelength. But it will shrink, as almost all materials do, as the temperature drops, by a few parts per million. So your 20-inch mirror, after you drop the temperature, is slightly smaller than 20 inches. Also, metal shrinks, but more than glass. So if your mirror is in a tightly fitting metal cell, as it gets colder, it's going to get more and more pinched. Or it may go from loose to pinched. Wood kind of varies more with humidity, and it depends on the type of wood as to how quickly it expands or contracts. But be aware that not everything is going to shrink at the same rate. So you can get a pinched mirror quite simply without having enough clearance around your mirror cell, and that's going to cause some nasty distortion. Just a few ounces of force on a mirror can distort the optical figure to the point where you can see it. You can see the effect. The effect kind of depends on where the force is being applied, though. I'm not sure why we lost the bottom of that slide. Interesting. So, we talked about thermal expansion in the sense of the whole mirror, but also understand that if parts of the mirror are cooler than other parts, those parts of the mirror are going to shrink. And therefore, that's going to distort the optical shape of the mirror. So this is what is responsible for that overcorrection as the mirror cools off at night. And this is normal because the edge of the mirror cools off a little bit more than the internal parts, and therefore the edge of the mirror gets pulled down very slightly, and that produces the same rough effect as overcorrection. The advantage of quartz is that, it expands 1/6 or contracts 1/6 as much as Pyrex. And so this overcorrection effect and other cooling effects from blowing fans on it, which I'll talk about later, are much, they're reduced by a factor of 6. But of course, it's a more expensive material. So this is the coma and collimation section at the top. How many of you have seen coma in a telescope? Most of you. Okay. How many of you use a laser collimator? All right. How many of you collimate with a star? You know how to do that. Very good. I'm going to talk about that a little bit for those of you who don't know how to do that. So coma is a distortion that is seen away from the optical axis, which is that center line that should go through the center of your eyepiece. It's seen away from the optical axis, off to the sides of the field. and it's produced by the primary mirror and occasionally by eyepieces. And it takes this form. This is an in-focus and an out-of-focus image of a little bit of coma with some atmospheric distortion added in this simulated image. So this is slight coma, and it's kind of hard to tell what's going on here when it's slight. This is moderate coma, and we see a definite bulge on the top side of this defocused diffraction pattern. And severe coma shows an obvious sort of fan shape. In this case, the tail of the coma, we call it, is pointing up. So one way to distinguish coma is that it's going to look just pretty much the same on both sides of focus. There may be other aberrations stacked on top. So if you see this characteristic shape on both sides of focus, you can be pretty sure that it's distortion caused by coma. And the reason is, if the optical axis is tilted a little bit off, on both sides of focus, it's tilted the same way. So you see the same type of distortion. It's quite possible that collimation is the only thing wrong with your telescope. And I hope it is, because it's pretty simple to fix if you've got reasonable adjustments. And learning to really nail it is going to generally produce the largest improvement in image quality and let you see what else is going on. So this is generally the first step that you use. It helps clear up a lot of things, and then you can see clearly after that, I like to think sometimes. First thing, has anyone ever checked the collimation of their laser collimator? Yes. Okay. How many of you have not? Admit it. I know it's a lot more than that. This audience isn't very honest with me. They are rarely perfect. So that is, when you stick in your laser collimator into the focuser, and you may or may not tighten down the screws, we'll get to that in a sec, and you turn that, you push it up against the top of the focuser, rack your focuser all the way in and turn that collimator. Does it draw a circle in your primary mirror? If it does, it's not collimated itself. And using it will probably just frustrate you. Oh yeah. If it stays very close to the same spot, then you've got a good tool for getting most of your alignment done. So, put it in the focuser, do not tighten the set screws, and push it against the top of the focuser. Spin it, and look for it to draw a circle. Then, rack it in and out and see if it moves significantly. There may be mechanical issues with the focuser. But I like to test everything with the focuser all the way in. But also, then there's less leverage for gravity to pull on it. So, another thing to think about. Tighten the set screws gently then and watch the spot and see if it moves. If it doesn't, you can use the set screws. If it does, I don't recommend using them. I just recommend pushing it against the top of the focuser and using that as your reference.
Can I ask you a quick question?
Yes.
When you collimate the laser, I've done it where, I should put on a V block, shine it about 30 feet away, and then put on a target, on a tree or something 30 feet away, and then I would adjust it from there. Is that accurate enough?
If what he's asking is, if you couldn't hear in the back, if you use a V block, which is a machinist tool for helping to align things and rotate the laser collimator in there, is that good enough? And the answer is yes, if the body of the collimator is machined properly. If the laser is centered and the laser is, accurately aligned to that, then yeah, that's a good test. But it's possible if the top part is, some of these collimators come apart. If the top part of it is cocked a little bit and the set screws tighten down, you push it against the focuser, it may kick it in one direction. So this is all very machining critical. But yeah, a V-block is a good way. So you've got the star in the center of the field. Remember the first rule. Okay? Got an eyepiece in. You can do this with a coma corrector in the focuser. You can try it without just to learn what coma looks like. But you really got to keep that star centered. When you put the coma corrector in, the nice thing is most of the coma goes away, and what you see residual, you can get rid of a little bit more easily than keeping that star precisely centered. So most of the time when I'm collimating, I've got a Paracore 2 or a SIPS, that's the integrated Paracore, in the telescope, and I just look at the star images, do that after I've done all my laser collimation. So the trick that you learn, and this is probably the most important part of this talk that I want to get across, is as you defocus the star, look for the direction in which that star starts to bulge. Don't defocus a bunch and look at the location of the secondary mirror shadow. That can be off if the secondary is offset. Watch how the star actually expands from a small little blob. If it pulls in one direction, that's coma generally. And that's what you're looking for at a very fine level when you're doing your last little bit of star columning. So this is far more sensitive than looking at that defocused shape. Covered most of that. So here we go. Here's how you collimate with a star. Here's a simulated star image of severe coma. You want to move the star in the eyepiece towards the tail of that coma. Okay, so in this case, if this was in the center of the eyepiece, we'd be looking in and it would move up in this direction and maybe slightly to the left. And you're doing that with the primary adjustment screws. This is after you've done the best possible alignment of the secondary with a laser that you can, assuming you have a good laser. That is step one. Step two, you can use your laser to align the telescope as good as you can. And step three would be looking for these small amounts of coma with your eye, with an eyepiece. When you've got it nailed, the star is going to expand in this beautiful circular manner. It's not going to pull off to one side, and it's going to be symmetrical. And then you know that pretty much down to the quality of the scene that you've got that evening, the quality of the atmosphere and the stillness of the air, you're collimated close enough that you're not going to see any degradation in your images. Of course, then you may move your telescope around and the collimation may shift, depending on the quality of the structure and how things are put together. And you may find yourself tweaking it throughout the night. For the best quality images, I do that. It's just fine. Mechanical structures aren't perfect at holding collimation. Some are better than others. If you are serious about this, you can kind of do it mentally, but you may want to go back and have someone help you do this and turn the screws that control the tilt of your primary and map the directions that moves the star. Then if you have that map with you, you can do it by yourself. You can say, okay, here's the star, it needs to go this way. Go down, make your adjustment, knowing which screw to turn, which direction, go back, and after about 4 or 5 iterations, you're going to have it really close. It's not that difficult. So getting rid of this nasty coma will help reveal the other things that may be wrong with the telescope that I'm going to talk about now. All right, here's a brief tutorial on pinched optics. Generally what you're going to see is this triangular shape. And it may be very subtle. So I recommend racking in and out of focus and watching the star expand. And if you see any hints of triangularity, look very closely. See, on one side of focus, does it reverse? This triangle will flip over, and the point will be up here. That's the difference between this type of optical issue and coma. Coma stays the same on both sides of focus. Pinched optics, that pattern is generally going to reverse, as will another aberration we'll talk about in a minute called astigmatism. If you really have a nasty pinch, I've seen it cause global astigmatism, like a lot of astigmatism that blots out everything else. But it has to be a really bad pinch. In this case, the sling supports were being pulled in against the mirror by the force that was being put on the sling. Another thing that can masquerade as this is how many of you have 3 fans on your telescope? Okay. Depending on how the cooling works for your instrument, you may get a triangular star shape from your 3 cooling fans because it's cooling 3 areas of the mirror more than the rest of it. The test for that is to rotate the mirror and watch it over a few hours. If that pattern goes with the mirror and then goes back, it's likely due to the cooling issues from those fans. Next we'll talk about astigmatism. I assume that you've all seen astigmatism in star images. Right. Okay, everybody's tired of putting their hand up, I'm sorry. That's another optical aberration. And what we see is on the inside of focus, we have sort of an elongated star in this direction. On the outside of focus, it might go in this direction. And those might be reversed. It just depends on how the mirror is being worked or what the problem is. As we defocus more, the image gets a little bit rounder. It's harder to see. So this is easiest to see close to focus. The same with coma, the same with pinched optics. You don't want to rack the focuser up to its limit and look at this giant image and try to figure out what's going on. Look close to focus and go on both sides of focus and watch the star. If it does this, then this, then this, chances are that's some astigmatism.
How much power should you use?
It's a good question. We want to use enough power to not have a small exit pupil, So medium to high power is generally going to be best for seeing these things. That's a good question, because I should have said that at the beginning of the presentation. The worse astigmatism gets, the more the image is going to look like a line on the other side of focus. So if you see a slight little bit, that's somewhat common from a variety of causes, including thermal issues and just having hot air in the telescope. But if it gets to becoming very severe lines and you don't get a good quality star image in focus, that's severe astigmatism, and you should really look for the cause of that closely. How do we determine if
Doesn't it tend to give you a cross when you're in focus?
if it's really bad, you'll get a cross image when you're in focus, yes. If it's really bad, you'll get a cross focus when you're imaging in focus. That's really bad. Otherwise, it's a kind of a subtle, it could be a subtle thing. But it does do great images. So we're going to talk now about the alignment of the astigmatism. We're trying to figure out, is this astigmatism in my primary mirror? That's the worst place it can be from, because that's going to cost the most to fix, unfortunately. But I find that most of the time it isn't. We want to look and see the alignment of this astigmatism. Is it aligned with the optical axis, aligned with the tube? I have a picture that shows this in a minute. Then we want to rotate the primary mirror in the cell. And of course, watch, does the astigmatism rotate with the primary mirror? If it does, we need to take another step here. So, if it does rotate, we have three possibilities. We have the optical figure of the glass, the actual shape it's been polished from. We have thermal distortion, which is some part of the mirror has been cooled more than another. Therefore, the mirror is warping itself until the heat redistributes itself within the glass. And we also have the possibility of strained optical glass. That is, glass that was made and wasn't properly annealed. That very often can go astigmatic and produce astigmatism while it cools. But that actually goes away as the mirror catches up and equilibrates. So you want to watch that astigmatism that you see over a few hours after you rotate the primary mirror. If it goes back to where it was, it's kind of obvious that you probably got a cooling issue or something due to the structure. Something, the wind blowing through the telescope can do this, creating a particular wind current that cools a part of the mirror more than another. It's common, and it happens quite often. And if it goes away, if it travels with the primary rotation and then it goes away, it's quite likely caused by some strain within the glass. And there's nothing you can do about that other than completely destroying the mirror, having it annealed, reground, refigured, and repolished. So most of the time you just live with it. Unfortunately, there's a lot of poorly annealed glass coming out of Asia right now. In smaller telescopes, let's say. There's a lot of them that I've just said, no, I'm not going to work on these because there's too much strain in them. It's not worth putting your money into something that might actually change shape in the future. That's the other problem with strain. The mirror shape may not be stable. It's like having a spring within the glass. And if something happens to it, it can creep over time or it can suddenly change shape. If the astigmatism goes away when you rotate your mirror, hallelujah, you just fixed your problem because you had a slightly pinched primary. It's simple things like this that can solve the problem. And if it always rotates with the primary and does not go away over the course of the night, then chances are it's in the primary shape, and the only way to do that is to polish on the mirror and polish it away and fix the shape. So this is an example of my own screw-up involving fans and cooling. This is a 16-inch scope I built years ago. Here are two fans in a line behind the 16-inch primary mirror. I've also got two more cooling fans on the bottom blowing on the bottom edge of the mirror. And this is cooling the primary very unevenly. And I would see astigmatism every time I had the scope out, and it would gradually go away over the course of the evening as the mirror got cooled down. So I'm not sure if it was from just the edge fans or just the back fans, but either one of those is not such a good idea. If you put three fans across here, it's going to cause the mirror to kind of fold on itself until it cools off, and that will cause some significant astigmatism. So, to distinguish other causes, we've talked about how to rotate the primary mirror. Now, one indicator that you have an issue that's probably not the primary mirror itself, and maybe a structural problem or a secondary mirror problem, is if the astigmatism, which I depict here in these simulated star images, looking in at eyepieces, this is my 20-inch f3 here a few years ago. if you see the pattern that's a line like this, you see here's the optical axis, the line coming out of the primary.